Hi folks, I understand that some of you are still having problems with the hydrolysis of salts. So let's clarify right now. First of all, let's remind ourselves about the concept of acid and base according to Bronsted-Lowry, acid being donators of protons and the base being acceptors of protons. And we say that the acid is strong when it has a strong tendency to donate protons. And the base is a strong base where there's a strong tendency of accept protons. Let's remind ourselves that the relationship between Ka and the pKa is an inverse relationship. So every time that we have a high Ka, the pKa is going to be lower. So the higher the Ka, the lower the pKa. And we know that the stronger the acid is, the higher the Ka value for that acid. Let's look at this scale here from the right side, from the left side to the right. Start with the strong acid to very weak acid. It's a continuum there, and we have the opposite comes from the strong base and the very weak base. Let's say, for example, HCl. HCl, we say that's completely dissociated. In reality, it's not completely dissociated, but for all practical purposes, especially in this class, we can assume that it's completely dissociated. But still there is a little bit of molecules of HCl that did not dissociate, but the equilibrium constant is so high, 10 to the power of 6, that the pKa would be -6. There is no meaning for us here, so we can consider that completely dissociated. So that's a very strong acid. As a consequence of that, the base, the conjugated base Cl- is a very weak base, because it does not capture protons to be coming back to HCl very easily. So a very low tendency of Cl- to capture protons, to accept protons, and becomes HCl. The flip side of it, let's do the hydroxide. Hydroxide is a very strong base. Sometimes we say sodium hydroxide is a strong base. Sodium is actually just the conduit of the hydroxide. The hydroxide itself is the strong base. This hydroxide has a very high tendency of capture protons and they become water. Therefore, water is a very weak acid. So hydroxide, very strong base. Water is a very weak conjugate acid. And we know that because we discussed in class that very, very few molecules of water dissociating in H plus and O minus. All the acids that have in between, we can consider that weak acid or can moderately weak acid and compare them. For example, here we have pyruvic acid. Pyruvic acid dissociated to give pyruvate. We talk a lot in class about acetic acid that dissociate to give acetate. And also, we mentioned many times ammonium that dissociated to give ammonia. So all of those are weak acids. Pyruvic acid, acetic acid, and ammonium. They are all weak acids. But within them, which one are weakest, the weakest one? Which one is the strongest one? For example, we look at that. For that, we look at the pKa. Because the lower the pKa, the higher the Ka. Therefore, the stronger the acid is. I'm not saying that pyruvic acid is a strong acid. I'm saying that pyruvic acid is stronger in this group of other, relatively compared to other acids. It's a stronger acid. For example, it's stronger than acetic acid. But both of them are weak, or we can call moderately weak acids. So the group here, the weakest of all, is ammonium, which has a pKa of 9.3. Now let's go back to the issue at hand, that's hydrolysis of salt. We put a NaCl in water. We have to remember where this thing comes from. NaCl comes from sodium hydroxide, and the Cl part of it coming from hydrochloric acid, HCl. So Na is just an spectator. We don't have to care about that because it not accepts protons, it does not donate protons, Na+. Cl minus, on the other hand, is a conjugate base of HCl. And HCl is a very strong gas. Therefore, Cl minus is a very weak conjugate base. It's a very weak conjugated base. It's not going to accept the protons and becomes HCl easily. Therefore, we do not consider that hydrolysis is significant in this particular case. So, if you have a salt that comes from a strong base, from a strong acid, then we put that salt in water, hydrolysis is not an issue. If you put another type of salt, like for example sodium acetate here, sodium again is an expectator, but acetate comes from acetic acid. Acetic acid is a weak acid, so therefore acetate is a stronger conjugate base. Not strong like hydroxide or things like that, but it's strong enough that can undergo hydrolysis. Therefore, in a situation like that, first thing we do, we build up the equation of what's happening here. Acetate is undergoing hydrolysis, and it becomes acetic acid and hydroxide. And from that, we can calculate the amount of hydroxide, for example, and determine the pH of the solution. If you know some other elements, how much, what's the initial concentration, so on, you can calculate that like we did. I think it was problem 25. Now, ammonium bromide. It comes here from bromide. Bromide is a HBr, is a strong acid. So therefore, bromide is a very weak base. We don't have to worry about that. But ammonium is a weak acid. And therefore, we have to look at that and to see what happens with ammonium here. Ammonia is going to undergo hydrolysis, and it's going to generate ammonium hydroxide and H+. Therefore, we can calculate the pH, if you know the concentration of ammonia, by doing that kind of calculation that we did in problem 25. When I used to teach this subject at high school, in chemistry in high school, I would give a hint to the students to check before they do the calculation to have an idea where this pH is going to be landing. Listen, this is not an accurate statement, but it's very practical that I gave to the students that are taking the STA equivalent at that time, because they don't have much time and they don't want to make calculations and get the wrong numbers. What I would say here is that it's a very simple way of thinking that we look at the stronger prevails in the hydrolysis. Here we have strong and strong, so no one prevails, the pH is going to be 7. Here we have another case now, sodium acetate. Sodium is strong, comes from sodium hydroxide, is the stronger part, right? And acetate comes from acetic acid, the weak part. So I would tell the students that the stronger prevails on the hydrolysis, so therefore if the stronger is a hydroxide, then we're going to have a pH that is alkaline. So the pH here is going to be above 7. Listen, what's happening here is not that. What's happening here is the acetate is undergoing hydrolysis, but gives you some hint to check your answer on your question. Am I going the wrong direction? If I put this salt in water, do I expect that this pH is going to be above or below or equal 7? That if you think about it, the stronger prevails in the hydrolysis, you can already estimate where the pH is going to be landing. So lastly, we have NHBr. NHBr comes from a strong acid and a weak base. So the strong prevails on the hydrolysis would tell you that this is going the acid is strong, therefore the pH is going to be below 7. So when you do your calculation and at the end, if you get something that's not below 7, then we know that we are doing something wrong. Okay? So I think that this is kind of an important hint that you use, although we know that what's happening here has nothing to do with the strong. What's happening here is that the ammonia is undergo hydrolysis and therefore capture protons, releasing protons, and that release of protons is going to reduce the pH of the solution. Okay, so we can go back and look at that. NaCl, no hydrolysis, pH 7. Sodium acetate undergo hydrolysis and captures protons from water and that water that gave you protons remains as OH minus. Therefore, the pH is going to be increasing. And finally, ammonium bromide, that's going to donate the protons, and water captures the protons. And we know in this class that in reality it becomes H3O plus hydronium. But for all principles, we use the simplification of protons H plus. So I hope that's crystal clear now, and good luck in the exam today.